Hello, my name is Kyle Rojek, and this video is going to be part 1 of exam 3. So to start out, I'm going to be explaining the Lewis relation. So the Lewis relation relates heat transfer and mass transfer for any geometry and any velocity to the volumetric heat capacity. And in this problem, we'll be talking about moist air. And so we start out with our two-dimensionless groups, the Nusselt number and the Sherwood number, which are found using dimensional analysis and the Buckingham pi method. And the Nusselt number is equal to our heat transfer coefficient multiplied by some distance over our thermal conductivity. And the Sherwood number is equal to our mass transfer coefficient multiplied by some distance over our diffusion coefficient. So we can see that these two dimensionless groups have similar styles in terms of that it is some transfer coefficient multiplied by some distance over a parameter without convection. And it is determined experimentally that our two models share similar coefficients, where the Nusselt number is equal to A times the Reynolds number risen to a power B, with the Prandtl number risen to a power C. And the Sherwood number is similar, but it is the Schmidt number risen to a power C. So next we divide the Sherwood by the Nusselt number. And that gives us our mass transfer coefficient multiplied by thermal conductivity over our diffusion coefficient multiplied by our heat transfer coefficient. And then that is then equal to our model. So these values cancel each other out, and then it is left with the Schmidt number over the Prandtl number risen to a power C. So the Prandtl number is equal to our viscosity over density multiplied by our thermal diffusivity. And the Schmidt number is equal to our viscosity over density multiplied by our diffusion coefficient. So dividing these two values, we get the thermal diffusivity over the diffusion coefficient risen to a power C. And we know that the thermal diffusivity is equal to our thermal conductivity over density times specific heat. And so plugging that into here, we get K over rho Cp times the thermal diffusivity risen to C. And it just so happens that by nature, that for moist air, this value is equal to about 1, and this right here is our Lewis number. And so when we multiply rho Cp over to the other side, we get our thermal conductivity over the diffusion coefficient is equal to rho Cp. And so we can use that over here to isolate our mass transfer coefficient and heat transfer coefficient. because K over DAB is then equal to rho CP, and that is then equal to 1 over rho CP. And this right here is known as the Lewis relation. So next, we'll be using the Lewis relation as part of an energy balance to be able to determine the relative humidity from wet and dry bulb temperatures. So we know the Lewis relation relates mass transfer and heat transfer. So we have our mass transfer coefficient and our heat transfer coefficient. So starting with the mass transfer coefficient side of our energy balance, we need a molar driving force. And that is expressed as the concentration of water vapor at the surface of our wet bulb, subtracted by the concentration of water vapor in the air. And this right here is going to be our flux, which has units of moles per meter squared per second. And also on this side of our energy balance, we need a heat source so that the water vapor is able to evaporate into the air. And that is given by lambda, which is the heat of vaporization, and that is in units of joules per mole. And then on our heat transfer side of the energy balance, we need a temperature difference. And that can be expressed as the temperature in the air subtracted by the temperature at the surface of our wet bulb. And so what this energy balance shows us is that the heat being transferred from the air to the surface of our wet bulb is equal to the thermal energy that is required to evaporate our water vapor from the surface to the air in our wet bulb. So next, I will be explaining the relationship between adiabatic saturation temperature and our wet bulb temperature. So first, we start out with our infinitely long, perfectly isolated tube. And this tube has a film of water across the bottom that is being continuously pumped. And we'll call this temperature of the water TW. And our tube also has a stream of air flowing in and out. And we have our mass flow rate of the air, our inlet temperature of the air we'll call T1, and also in this air is our partial pressure of water vapor, which we'll call P1W. Then in the outlet stream, we have our outlet temperature and our outlet partial pressure of the air. But this partial pressure of the water vapor in the air is equal to the saturation temperature of water vapor at TW. And so now we want to make our energy balance. And since this tube is at steady state, our enthalpy in is going to equal our enthalpy out. So we'll start with the enthalpy inside of our balance. And with that, we start with our mass flow rate of air. And in an enthalpy equation, we need our heat capacity. So we have our heat capacity, Cp, and then that is multiplied by our inlet temperature, since this is enthalpy N, with respect to a reference temperature, but we'll have our reference temperature equal to 0. So this is just T1, our inlet temperature. Next, we need to set our enthalpy scale so that our enthalpy is equal to 0. And we do that by adding in our concentration. And so what this does is allows us to add our heat of vaporization, which is lambda, and we'll have this in joules per mole. And then next, we want to add the concentration. So that is going to be equal to our inlet partial pressure of water vapor in air over RT. And so now we want to have, so what this right here gives us is moles per meters cubed, but it's moles of water vapor in air per meters cubed. So now we want to multiply that by moles of air and water vapor over our meters cubed. So we have RT, and we want the average molecular weight so that our mass flow rate of air is able to cancel out. So we have that on the bottom. And then we also want to have the total partial pressure of air and water vapor. Alright, so this is our enthalpy N equation. And next you're going to make our enthalpy out equation. And that's going to be very similar other than a few minor changes. So we still have our mass flow rate of air multiplied by our same heat capacity, but instead of our inlet temperature, we want our outlet temperature. And with the same heat of vaporization, but instead of our inlet partial pressure, we have our saturated partial pressure of water vapor at TW. So we'll call that P2W over the same RT, and the second part is the same. Total partial pressure over our average molecular weight. So next we set these two values equal to one another. And so that allows us to cancel out our mass flow rate of air and the RT, and leaves us with our specific heat times T1. Oh, and yep, times T1. And then our partial pressure of water vapor, the total times the average molecular weight. And that is equal to our outlet the equation. Got a plus right there. And so next we want to massage this out so it can look a little similar to our wet bulb temperature equation that we had earlier. So this is going to be equal to lambda over our total partial pressure, the average molecular weight, with our partial pressure difference, and that is going to be equal to our heat capacity with our temperature difference. T2 minus T1. So this is the equation that we get for our saturation temperature, and I will massage it out a little bit so that it can relate more closely to our wet bulb temperature equation. So now I'll be showing how our wet bulb temperature energy balance that we solved for previously, which is right here, is very similar to our adiabatic saturation temperature, which we just solved for. So to start out with our wet bulb temperature equation, we use the Lewis relation by dividing H over Kc, which is equal to our volumetric heat capacity. And then we look at our concentration difference. So we see that our concentration at the surface correlates to our saturated partial pressure of water vapor leaving our insulated tube. So we have, and that is classified as P2W over RT, subtracted by our partial pressure of water vapor coming into the tube, which is P1. And then we have our density, which can be correlated to our total partial pressure and the average molecular weight. Over RT. And then our temperature difference. And so our temperature in the air correlates to our inlet temperature, which is T1, and the temperature at the surface of our wet bulb is equal to our outlet temperature. And so we cancel out all of our RTs and move our total partial pressure and molecular weight average keep everything else the same. Oh, I forgot our heat capacity up top. So we have our heat capacity with our temperature difference. So as we can see here, this equation is identical to our equation we just solved for. And what this tells us is that the adiabatic saturated temperature, which is T2, is equal to our